Let us start lecture 9, and the topic for the lecture 9 would be concept of equilibrium. We will continue that particular discussion, and now we will start quantifying entropy on the basis of the experiment what we have carried out in lecture 8. Now, if we see lecture 8 experiment, the experiment what I have explained in the lecture 8 is basically we are talking about irreversible expansion as well as irreversible compression during evaporation or condensation respectively. We are going to another state from state 1 to state 2, and when we are going for evaporation, we allow the evaporation till 1 mole of converts to vapor, 1 mole of liquid converts to 1 mole of vapor, and after that we bring back the pressure to P external, which is the saturation vapor pressure. So, that means it will again come to the rest, which is equilibrium. Now, in the same situation happens in case of condensation. We increase the pressure to a finite amount in case of irreversible process. We allow condensation till 1 mole of vapor converts to 1 mole of liquid, and after that we bring back the pressure to P external. Okay. So, that means it comes to the same saturation vapor pressure, which is function of the temperature of the reservoir, entire thing which is system plus the reservoir. Okay. So, it is basically cyclic process. During cyclic process, we have permanent change on the external agency due to irreversible process, and if we take the cyclic process reversibly, that means the change in pressure during evaporation or during condensation, that change in pressure would be infinitesimally small, and smaller the change, the higher would be the tendency of the system to seem like be in equilibrium, okay, or be in under rest. So, that is basically reversible, and during reversible process we could see that the total change in total change due to the cyclic change, that means whenever there is a 1 mole of liquid converts to 1 mole of vapor during reversible process, immediately we bring back the pressure to saturation vapor pressure, which is P external. Similarly happens in case of condensation, we increase the pressure by infinitesimal amount during reversible process and bring back the pressure to bring back the P saturation or the P external, so that no more condensation or no more evaporation happens, and that time that same cyclic process we see that there is no permanent change on the external agency. So, the total work, if we consider the reversible process, is nothing but, so we are considering the evaporation as well as condensation process. Refer experiment, which is experiment in lecture 8. Okay, which is P external Vm, this is plus, and minus P external Vm, this is minus with reference to system. Okay, fine. So, this is the maximum work evaporation, and this is the minimum work. To be done on system, and this is done by the system. Okay, fine. And this happens in case of reversible cyclic process. The system comes back to its original state due to the cyclic process. Now, when it is reversible cyclic process, the change on the external agency equal to 0. But if the same thing happens irreversibly, so then my work would be P external minus del P V m, and here would be minus P external plus del P V m, okay, in case of evaporation, and this is condensation, and we are taking reference system as a reference. So, this is irreversible cyclic process, okay, and the system comes back to its original position where it started during the, and let us say we are starting evaporation process first. So, it started from one state to another once evaporation of 1 mole of liquid happens, and condensation takes it to the initial position where we have taken 1 mole of vapor to convert to liquid, and then we immediately brought back the saturation vapor pressure. So, it came back to the same temperature, pressure and volume after cyclic process. So, this process, the change on the external agency is equal to del P V m 2. So, that is what we have understood from lecture 8. Now, let us try to quantify. Now, if we consider, let us say, a closed system, because that was a closed system, fine, and let us in the beginning, let us consider fixed composition, and we are considering only the mechanical work, okay. We are considering these are the conditions, and we are taking it as a isothermal process. So, the same as experiment in lecture 8. Now, I can write a general equation del U equal to Q minus W. If it happens through irreversible process, then I can write del U equal to Q. I can write this is, let us say, let us consider this is irreversible evaporation. Now, this I put it as reversible by minus W, and since we know the reversible expansion, the work done would be the maximum, we can put max. This is reversible evaporation. So, this is, I can say this is irreversible heat, and this is work done during irreversible process. Now, since this is isothermal, since that is why this will be 0, does not matter whether it is irreversible or reversible, because U is a state function. Now, I can see that if I make a difference, this is 2, this is 1. So, if I make a situation 2 minus 1, I can write Q reversible minus Q equal to W minus minus W. This is an interesting equation. So, let us understand this equation. So, had it been reversible process, I would have gotten maximum work, which is nothing but P external Vm. Okay. This is the maximum work I would have expected. If it is irreversible, then I know that some amount of work would be lost. And when the some amount of work is lost, and these works are all positive work because the system is doing the work. So, I am getting less work during irreversible process from the system. So, the amount of work that is lost is W max minus W. So, this is nothing but lost work, and this work energy has to convert to another form, and here I am seeing that the amount of lost work is actually equal to the Q reversible minus Q, and where Q is irreversible heat. And in both the cases, whether it is a irreversible expansion or reversible expansion or evaporation related situation, both the heat is actually entering into the system from the surrounding, okay, which is the heat reservoir. So, I could see that during reversible process, Q reversible would have been the maximum heat that the system would have acquired from the reservoir had there been 1 mole of vapor formation, okay, during reversible evaporation, and then immediately we bring back the pressure to saturation P external. So, it will come to another state of rest, fine. So, that means this amount of heat, so that is the lost work. So, that lost work is actually converting into certain quantity of heat, and that heat is actually get stored into the system. Okay. So, this is basically nothing but converted heat from lost work, which is stored in the system. Okay. System is what? Water and plus vapor. Okay. So, there it is getting converted, fine. So, now let us calculate the entropy change during reversible as well as irreversible process. So, entropy change, let us say I am calculating del S system, and both the cases I am considering reversible evaporation and that too isothermal. So, we have seen that this would be nothing but what will be the amount of heat that would enter into the system due to this reversible isothermal expansion evaporation of 1 mole vapor formation. So, this would be equal to Q reversible by T, and here heat quantity with respect to system is nothing but the positive. So, that is what this is positive. Now, I can calculate del S reservoir. So, the amount of heat that would be lost by the reservoir would be minus Q reversible by T. Okay. So, if I try to calculate del S total, which is del S system plus del S reservoir, would be equal to Q reversible by T minus Q reversible by T. So, this becomes 0. So, the total change in entropy of the system and the reservoir is 0. So, I am not able to create any entropy, but there is an interesting physical significance of these two situations. So, now here you see entropy is created, and you see here entropy is lost. So, I can say that reversible process entropy of total should be 0 and entropy created somewhere is equal to entropy lost somewhere. So, that means there is no net creation of entropy, rather than entropy shifts its position rather. So, entropy of the reservoir is lost and the same entropy is gained by the system. So, this is basically for a reversible expansion system or reversible evaporation or reversible expansion of 1 mole of vapor formation, and that too happening in isothermal mode. So, let us see what happens in case of irreversible process. Reversible, and this is also isothermal. Okay. Evaporation, fine. So, del S system would be what? Because if the same state change happens, same 1 mole vapor formation, 1 mole vapor formation, the del S system would be equal to Q by T. Here also the heat will enter into the system from the surrounding and this will be positive, and this Q is basically the irreversible heat, which is less than Q reversible. Fine. Now, what will be the reservoir? Would be equal to Q by T minus. Now, question is whether this is true. This is correct. Whether there is any other form of entropy that is there in the system. Okay. In order to understand that, let us go back to this. Okay. So, now we know that same change is taking place state 1 to state 2. One is happening in a reversible mode, another is happening in an irreversible mode. And in case of irreversible mode, I see that the some amount of work is lost. And at the same time, from this equation, I could also see that that lost work is converting to heat, and that heat is contained in the system. So, that means there should be one more term associated with it. So, del S system, I can say this is apparent. So, that means this is not true. Okay. So, that means actual would be Q by T, that is basically the heat that is entering, and plus the lost work that is converted to heat that is stored in the system, and that heat stored in the system will be giving some amount of entropy. W max minus W by T, or I can say Q by T plus Q reversible minus Q by T. Okay. So, I could see that the system has an extra entropy that is created, but now let us see whether what would happen if I do the simplification. So, I would see that finally it turns out to be this. So, this is basically irreversible process, okay, for the same state change. Now, this is del S, sorry, you just put that del S system reversible would be equal to Q reversible by T. So, that means whether the system having a change through reversible or irreversible manner, both the cases entropy change would be same if the state specified are same. Okay. So, same thing is coming up. Okay. So, that is what the entropy is. So, this suggests that entropy is a state function. Fine. So, once we have this, let us calculate what is the total entropy of the system. Would be equal to del S system plus del S reservoir equal to Q by T plus Q reversible minus T, sorry, Q by T minus Q by T, which is equal to Q reversible minus Q by T. Fine. In fact, so this is nothing but extra entropy created due to irreversible process. Now, what was del S total? This is irreversible. What was reversible? We saw that it was Q reversible by T minus Q reversible by T equal to 0. So, that means this extra entropy created, and this quantity you see is always then greater than 0. So, that means during irreversible process, the total entropy if we try to consider. So, I can take it as a surrounding, I can take it as a system. So, that means the total considering system and surrounding, there will be always creation of entropy. And this quantity I can write it as equal to del S irreversible. So, I can write these equation as del S system equal to Q by T plus del S irreversible. So, this is indicating the entropy created due to irreversibility. Okay. So, I could see now I can actually have a judgment now. What would be the degree of irreversibility? And this degree of irreversibility will be decided by what will be this loss of work. If we get the all work is lost like free expansion, everything would convert to entropy. So, we will not get any quantity of heat or any quantity of work from the system. So, that means entire work will be lost. So, but if we have a degree of irreversibility is less, then we would definitely get some amount of work from the system, but that would be less than the work carried out through reversible mode. So, in fact, we will always see the work due to irreversible expansion or irreversible evaporation would be always less than the work due to reversible expansion or evaporation, the kind of situation what we have seen. Now, the similar thing we can actually get, we can prove if we consider condensation. So, condensation if I see, so which is isothermal, fine, isothermal condensation, let us say reversible, same experiment what we have explained in lecture 8. So, same thing if we go by del S system, I will just quickly go through. Del S system would be equal to minus Q reversible by T, and del S reservoir would be Q reversible by T. This will be positive because heat will be lost by the system during condensation. So, then del S total would be equal to 0. Now, if I try to see isothermal condensation and irreversible process del S system would be, now try to understand, minus Q by T, because that time the heat lost would be minus Q, and this would be equal to plus Q minus Q reversible by T. This is actual. Why? Let us understand this. This is minus, we understand that the heat is left by the system to the surrounding during condensation. Now, this part we have to understand. Now, during condensation, the work that is done on the system is minimum. So, here work is what W minimum, not maximum. So, if that is the minimum, then corresponding Q reversible during condensation should be less than Q irreversible. I will just put IRR in case of irreversible. So, this will be the situation. Now, when the heat is actually released, fine, by the system, so then some amount of it is lost, at the same time some amount of work is also lost. So, that work lost would be reflected here, and since Q reversible is lower than Q, so that is what this amount of work would be converting to heat, considering it is a condensation, it is a minimum work. So, that means that any work done via irreversible process would be more than the reversible compression, okay, or reversible condensation. So, that is what this is coming like this. It was not same as what we have considered in case of reversible. So, this is this, and then system, this is S surrounding or reservoir would be equal to plus Q by T. So, now we can say del S total, and here it is reversible for the same state change, would be equal to Q by T minus, first I am putting all the system, plus Q minus Q reversible by T plus Q by T. So, it becomes Q minus Q reversible by T, and here since Q irreversible, which is nothing but Q, this again greater than 0. So, which can be written as del S IR. So, that means this is irreversible entropy change. So, now I can write this system part equal to minus Q by T plus irreversible. So, I could see that even in the condensation process, irreversible mode, isothermal mode, I would still create some amount of entropy, total entropy, which is reflected by this and which will be greater than 0, fine. So, in both the processes, I could see even if it is condensation or expansion or evaporation, I would see that there would be always some entropy creation during irreversible mode, and the degree of irreversibility will be decided by how much of that entropy is being created, and more the entropy creation or the irreversible, higher the value of del S irreversible, higher would be the loss of work, and the maximum possible loss of work would be when W max, the total or W minimum, entire work is lost, then we will have the maximum entropy change. And interestingly, here also if you see, if you add it up, you will see it becomes minus Q reversible by T. Okay. So, then you see that whether it is running in a reversible or irreversible process, if the states are specified, I would have the same change in entropy. And that is what the differential mode. So, this S is always considered to be reversible heat change, okay, associated with the reversible heat change. I can write it as del S equal to del Q reversible divided by T. So, this is one of the concept that is coming up after we had those discussions. So, with this till now we are at least we can actually relate it to equilibrium. Now, let us say this goes to 0, this irreversible work, the irreversible entropy. Once it goes to 0, you see it leads to this. So, that means when the reversible process is happening, the system goes onto an equilibrium, I see the total entropy change is 0. Okay. So, this is also indicating equilibrium, fine. So, we will continue our discussion on this. So, let me stop here. Thank you very much.